Prime numbers are fascinating. They're kind of like the atoms of the mathematical universe. Just like atoms, they serve as the fundamental building blocks of larger entities. Any number greater than 1 can actually be expressed as a unique product of these prime numbers. For example, 12 can be broken down into 2 times 2 times 3. Similarly, 30 is 2 times 3 times 5. So, what makes prime numbers special? A prime number has exactly 2 divisors, 1 and itself. Take 7 for instance. It can only be divided evenly by 1 and 7. On the other hand, a number like 10 is not prime. It can be divided by 1, 2, 5, and 10. These prime building blocks are scattered throughout the number line, and honestly, they seem to pop up at random. This unique property of prime numbers makes them absolutely essential to mathematics. They're the keys to understanding the structure and behavior of numbers. And their importance? It goes way beyond theoretical math. Prime numbers are actually the bedrock of modern cryptography, helping to secure our online transactions and communications. The distribution of prime numbers is, well, a puzzle that's intrigued mathematicians for centuries. There's really no easily discernible pattern. They just appear to be sprinkled randomly across the number line. As we move further along that number line, primes become less frequent. So, to make sense of this, mathematicians have developed tools to estimate the distribution of primes. One such tool is called the prime number theorem. This theorem gives us an approximation of how many primes exist up to a given number. Basically, it tells us that primes gradually thin out as we explore larger and larger numbers. But despite these tools, the gaps between consecutive prime numbers still remain unpredictable. The twin prime conjecture, for example, suggests that there are infinitely many pairs of prime numbers that differ by only 2, like 11 and 13, or 29 and 31. And while this conjecture is still unproven, it really highlights the elusive nature of prime distribution. To delve deeper into the mysteries of prime numbers, mathematicians turn to a pretty powerful tool, the Riemann zeta function. Now, don't let the name intimidate you. The zeta function, which is usually written as zeta of s, is kind of like a special calculator. You input a number, s, and the function gives you a new number in return. The really intriguing part is how this function connects to prime numbers. That link is revealed through something called Euler's product formula. This formula shows that the zeta function can actually be expressed as an infinite product involving prime numbers. It's a bit surprising at first, but it's like finding a hidden passage that connects 2 seemingly different worlds. And this connection isn't just some mathematical curiosity. It gives us a whole new lens through which we can study the distribution of primes. By understanding how the zeta function behaves, we can hope to unravel the secrets of these fundamental building blocks. To fully grasp the power of the zeta function, we need to venture into the world of complex numbers. Complex numbers are an extension of the familiar real numbers. They consist of 2 parts, a real part and an imaginary part. Imagine a number line where, in addition to the usual numbers, we have numbers that lie above and below the line. These are the complex numbers. The zeta function operates on these complex numbers. We can visualize this function as existing on a complex plane, a 2-dimensional grid where each point represents a complex number. This plane becomes our canvas, and the zeta function paints an intricate picture on it. The behavior of the zeta function on this complex plane holds the key to understanding the distribution of prime numbers. Specifically, certain special points on this plane, called zeros of the zeta function, are of paramount importance. Remember those zeros of the zeta function we talked about? They are the points on the complex plane where the zeta function equals 0. These zeros are not randomly scattered. They seem to cluster along a vertical line on the complex plane called the critical line. The Riemann hypothesis, one of the most famous unsolved problems in mathematics, makes a bold claim about these zeros. It states that all the non-trivial zeros of the zeta function lie on the critical line. This might seem like an esoteric detail, but its implications are profound. The Riemann hypothesis, if proven, would have far-reaching consequences for our understanding of prime numbers. It would provide a much sharper tool for predicting the distribution of primes and would unlock many secrets about these fundamental building blocks. Why is the Riemann hypothesis so important? Because it connects the seemingly random distribution of prime numbers to the behavior of the zeta function on the complex plane. If we can prove the Riemann hypothesis, we can unlock a deeper understanding of how these prime numbers are scattered throughout the number line. The connection between the zeros of the zeta function and the distribution of primes is intricate and requires advanced mathematical tools to fully grasp. However, the essence of this connection lies in the fact that the zeta function encodes information about prime numbers in its structure. Proving the Riemann hypothesis would be a major breakthrough in mathematics. It would not only solve a century-old problem but would also pave the way for new discoveries about the nature of numbers and their hidden patterns. Exploring the Riemann hypothesis is a journey of discovery. It's like climbing a mountain, with each step revealing new vistas and challenges. Here's a possible roadmap for this intellectual adventure: Base Camp. Start with the basics of number theory. Understand prime numbers, factorization, and modular arithmetic. Intermediate climb, delve into calculus and complex analysis. These tools are essential for understanding the zeta function and its properties. Final ascent. Explore advanced topics like analytic number theory, L functions, and modular forms. These areas are at the forefront of research on the Riemann hypothesis. The Riemann hypothesis is a challenging problem but also an incredibly rewarding one. The journey towards understanding it is filled with beautiful mathematics and profound insights into the nature of numbers. Who knows, maybe you'll be the one to finally conquer this mathematical Everest.